The first part will be about the diffeomorphism group. I already said that yesterday that we will talk about the diffeomorphism group, and then never popped up. So today we definitely will talk about it. And then in the second part, I will talk about symplectic reduction. And then at the very end, if I have time, I will make some comments about complex geometry, but maybe that's, again, a bit too optimistic. So I prepared a little bit already so that we can go through some of the analytic difficulties right at the beginning. So we would like to look at the diffeomorphism group, and as a symplectic geometry, what we will look at is like actions of a group on a symplectic manifold, and usually of a Lie group acting, so that we can use the methods of differential geometry. So the first question is like, okay, like if you go to infinite dimensions, diffeomorphism group is the natural group that like pops up besides maybe some gauge transformations. So the question is that a Lie group in a natural way? And we already saw like these kind of problems in multiple instances that last week someone claimed he really wants to get rid of composition like as soon as possible. But if you want to look at the Lie group structure, then you can't get rid of it. So the problem is that the composition, which is the natural multiplication in the group, is a nice continuous map. But if you take the derivative at, say, you fix f and g, and then you change them slightly along some vector fields, what you see is if you take the derivative, then on one hand, you just take the derivative in the x direction. So you replace that by some vector field, and then you take the derivative in g. And that's where the problem comes in, because then you take the derivative of f in a certain direction of the vector field. So what you see is that you kind of lose a derivative degree there, because you take the derivatives of the points. So the upshot is that if you want to fix the degree of like the regularity of your diffeomorphism, say Sobolev or CK, then what you end up with is a topological group, which is a Banach manifold, but it's not a Lie group because the operation of composition is not smooth in your setting. The alternative approach is that we leave the Banach setting and really consider that as a nice Fréchet Lie group. But the cost that we have to pay is that we really leave our Banach setting and have to move to the Fréchet setting. And from a functional analytic viewpoint, it's actually not like a big move. Many results that you know, the open mapping theorem, the Hahn-Banach theorem, and many of the other theorems that you know from function analytic from Banach spaces also work on Fréchet spaces. There are some problems. Sometimes you have to pay a little bit extra, but there's not much, like on a linear level, there's not much problem going from Banach to Fréchet. The really difficulty comes in that sometimes you would like to use an inverse function theorem to kind of like straighten out something that is curved, and you want to make it like straight in some way. And that's usually done by some application of the inverse function theorem. And we all know that in a Banach setting, you have a classical inverse function theorem. You can like also nicely estimate how big the size of your invertible function is. So that's kind of like nice and beautiful and well known. And then you go to the Fréchet setting because you want to kind of like study your diffeomorphism groups as nice Lie groups. And then you read these papers, and then the only inverse function theorem that comes up is the Nash-Moser inverse function theorem. And I did the mistake in my PhD thesis to really read the paper of the Nash-Moser inverse function theorem. And it's a very beautiful theory, but I still don't really understand what is actually going on. It's like, in some way, you have like this, like the grading of the case, and then you kind of like jump down because you lose derivatives as here, and then you kind of go back, and that going back needs to be in some way nice enough so that you can like estimate the size of your domains, that you don't kind of like shrink in the limit. So that's then a Nash-Moser inverse function theorem is like way more complicated. And one of the problems is, for example, that you don't need only the derivative at one point, but you need the derivative in some neighborhood. And that's going to be like usually hard to estimate or like hard to calculate even for the geometric part. So that's just as a like a general thing. It's like sometimes as in life, there's just not an easy solution or like an easy choice. Like either you work in a Banach setting, then you don't get a Lie group, but you have a nice inverse function theorem, or you work in a Fréchet setting where you have a nice Lie group acting in a nice smooth way, but you don't have a nice inverse function theorem. And then sometimes, depending on the problems that you look at, one of the few points is easier and one of them is harder. So that's like about the analytic part about diffeomorphism groups. When it comes to symplectic geometry, diffeomorphism groups have another really huge disadvantage to some other groups, and that is related to the conserved quantities. And in symplectic geometry, these are called momentum maps. So what we have is some Lie group, infinite dimensional, acting on an infinite dimensional symplectic manifold. So I never really give like a definition what a symplectic manifold means, but you can just assume that like what we discussed last time is the linear version, and then you assume that like in some chart it looks like what we discussed last time. So that's like the setting, and we assume that the Lie group acting on a symplectic manifold and preserves the symplectic form. And then corresponding to that action, consider some point, and that point moves with the group action. So that's the orbit that you get from the group action. And associated to that, we get something to every Lie algebra element. We get a certain vector field on our manifold M, which is called the fundamental vector field. Of the action. So that's a vector field on M. So I have to give myself a point, and then I have to associate to that data, like a vector. So what we do is we move in a slight direction with the exponential map of the, like in a little bit in the direction of the orbit, and then we just take the derivative. In this picture, it's the fundamental vector field is just the vector field that is like along the orbits. So at each point, you get a vector field along that orbit. So that's the infinitesimal action that you get induced. And because the action was, we assume that the action preserves the symplectic form. If you take the derivative of what this means is that the Lie derivative of the symplectic form has to be 0. So now we use our Catan theory, or the Catan magic formula, meaning that we get formula of that form. By assumption in a symplectic manifold, this one is 0, because we assume our symplectic form to be closed. So what you see is that this form here, this guy, is closed. And the momentum map is, in some way, it's just like choosing a primitive of that form. Momentum map. The map from the symplectic manifold into the dual of the Lie algebra. And now we come like to the first problem in infinite dimensions. It's usually you don't want to choose the full dual there. Because like what you want, for example, is that if you have a free action, you want kind of something like as a surjectivity of the momentum map, at least on an infinitesimal level. So if you choose all of the like distributional dual, like the full dual usually, then you never have some results of like that the tangent map is surjective. So you usually choose this guy to be some subset of the full dual, and that you have to choose like depending on your problem. So that's not like the full dual, but it's something that is in duality to your algebra. And the equation that it has to satisfy is that if you plug in this fundamental vector field in your symplectic form, you can write this as d of the momentum map and then compare it with the Lie algebra element. That's the equation that you say, like, okay, we require a map of that sort that satisfies this equation. Okay, so now let's look at like one of these examples that we discussed already. Namely, we look at manifold with a volume form and a manifold, a symplectic manifold, so a finite dimensional manifold here. And then we look at the space of all embeddings of L into M. And we endow that with a symplectic form, which was roughly speaking just like formally written, was just we get the two vector fields, we plug them in the symplectic form, and then we integrate. So we discussed that already. And now on that space of embeddings, you have two actions. One of them is of the diffeomorphism group of L, which is by reparameterization, and then also one of them by M, by just like post-composition. So let's look at this action here. And you can calculate that this action is symplectic, so it preserves the symplectic form. So in order to calculate the momentum map, what you need to do is you need to calculate the fundamental vector field. So it's a fundamental vector field on the space of embeddings, and it's induced by a vector field on L. Sometimes it's a bit of a tongue twist. So we have a vector field on L, and that induced a fundamental vector field on the space of embeddings. And it's given by at the point, which is like say, some iota, which is an embedding. It's by post-composition, by pre-composition. So the metal vector field at that point iota is essentially we take our formula that I wrote up there. So it's by pre-composition. So essentially we get like the derivative. I should also write it like this: the derivative of iota, and then we just apply a vector field, and that gives us a vector field along iota. That says like how that changed. So in this case, the fundamental vector field is just the push forward, if you want, of that vector field. And then we have to dualize it. So it's not like a big surprise that you want to say like that the pullback gives you a momentum map. But we first have to discuss for that what is the natural choice of the dual space. Yes.
That's not really the meaning of momentum map. What does it mean, DJ?
So you just consider it as a smooth function, and then these ones are just like the exterior derivative. So that one you can think of that one as a one form on M with values in the dual, and then you contract there in the dual to get like really just a normal one form. And physically, maybe I should have said that earlier. Physically, for example, if you have rotation, then the conserved quantities give you the angular momentum. So it's like essentially what we know from Noether theorem is that to each symmetry we get some conserved quantities, and that's here that to each symmetry, which is this action that preserves the symplectic form, we get a conserved quantity, and that conserved quantity is encoded in this momentum map. Now we ask ourselves, what is in some way the conserved quantities associated to certain diffeomorphism actions. So that's like from a physical viewpoint what we do. Okay, so we need to clarify what is the dual. So the dual of the vector fields that preserve the volume form. And these vector fields with that preserve a volume form, we can identify them with certain n-1 forms. So what we do, if we have the volume form, we plug the vector field in this volume form to get a n-1 form on L. And because we assume that our vector fields preserve the volume form, what we see that we don't get all of them, but only the ones which are closed. So we need some pairing now of the closed n-1 forms with on L. So what a natural choice for the dual is then that we say we just use the one forms on L and then just pair them with this n-1 form to give us a full n form, and then we integrate that. So that's a natural choice. The problem is that we take here only the closed ones, so there will be a certain certain one forms. If you pair them, they will be 0. And these ones are exactly the exact ones. It will give 0, so we have to portion out so that we really get like a nice dual. So that would be a natural choice. And again, it's a choice that we have some freedoms. And in general, you would expect some form as like distributional one forms there for the full dual. Okay, so the point is, as I explained, the action is to push forward of the vector field. You would assume that the momentum map, which is kind of like a dual, which would be a map from embeddings into this space over here, should be a pullback. But there's nothing really that we can pull back. Like the only thing that we can pull back is the symplectic form, but that's a 2 form. And if I pull back, then I don't get like a 1 form there. So the point here is that if omega happens to be exact, so there's like a 1 form, then the momentum map is just the pullback of that 1 form. So that you can calculate, and it's essentially just playing around with this duality that you push forward the vector field, so you expect by duality that you get the pullback as the momentum map. So that raises now a big question, like what if our symplectic form is not exact? What can we do there? And there's a certain ways, like one of them approaches would be, for example, that we kind of like pull back and then kind of like have a reference form on L, and then we compare that to the pullback and like hope that it might be exact. And then what it turns out that was done by Cornelia, for example, with Francois, that you get like a momentum map, but it turns out to be not equivariant. So that's like in full generality, there's no way to really get an equivariant momentum map for the full group of diffeomorphisms. And there's one way out of this problem, and that's the following: is that we can think of that the dual geometrically. So we have the dual, which is 1 form modulo exact forms. So we can think of the 1 forms on L. We can think of that one as connections on a line bundle, or on a principal U1 bundle if you want, over L, where P is trivial. It's a trivial line bundle, and then you learn the first moment is that the 1 forms can you identify with the connections on the trivial bundle. And similarly, if you have that interpretation, and what we already discussed also is that the 0 forms have the interpretation as gauge transformations. And they act in the way that you would expect them to act, namely by just like changing by D. So that means if you take the quotient over there, we get the following interpretation of one forms modulo B of the zero forms. These ones are page equivalence classes. Equivalent classes of trivial one bundle over L. So that's the geometrically how you can think of this quotient. And now, of course, there's like a natural candidate. What you can do, you can just try to the trivial over there and consider instead of instead of looking at the equivalence classes of connections on a principal bundle over L that are defined on a trivial one, we consider all of them. And that space is usually called the Chern-Simons differential character space. And that's, depending on your conventions, it's denoted by H hat. And that's the space of classes. Principal one bundle with connection. That's a natural generalization of this dual space, but the problem, or on one hand it's a problem, on one hand it's the feature of the theory, is that this space is no longer a vector space. And in fact, there's some kind of exact sequence. You can think of these ones as the trivial, roughly speaking. We have the modulo, or the exact ones. They sit kind of as the trivial connections in there. And then we have something which is the Chern class. This one is the Chern class that classifies your bundle up to gauge transformations, and then you say like, okay, the rest are things on a trivial bundle that I can choose. So you see, in some way, it's like this guy here in the middle is very close related to that, but it gets kind of like integer values that you can add to it. And it turns out that it's a nice Lie group in infinite, like an infinite dimensionals, and this an abelian Lie group, and the Lie algebra associated to this is then the space of one forms modulo exact ones, which essentially follows by just taking the derivative of this exact sequence, and here we get something discrete. So the upshot now, so the reason why I'm discussing these bigger groups is because it gives us a little bit more freedom to play with. And in fact, we have the following result, that assume that, here we assume that omega was exact. Now we assume slightly like weaker, or like actually considerably weaker condition, namely that we have what is called a pre-quantum bundle of the symplectic form. So that means that the curvature, so we have a principal U1 bundle over the manifold and a connection on that bundle, such that if you take the curvature of the connection, you get your symplectic form back. So that's here in this case, that would be saying we can take the trivial bundle and then just take the preform as the connection. But here we don't say anything about that this bundle needs to be trivial. And if you assume it like this, then we can define now a momentum map from the embedding space into this group of gauge equivalence classes of connections. And that's essentially what you would expect. You have the iota, and you just take the pullback of the bundle, so you get a bundle over L, and you take the pullback of the connection to get a connection on that pullback bundle. And that gives you then, if you take them up to equivalence classes, gives you a well-defined element in the space of gauge transformations, like gauge equivalence classes. And this one satisfies an equation that looks very similar as above, namely that if you take the fundamental vector field and you plug it in your symplectic form, so over there we had like that we get d of j, but a d of j in this case would be something that like takes values at a certain element of the target group. So we have to move it back by j and pair it with c. That's this guy over here, what is called the logarithmic derivative. And that's what we saw today in your talk. It's like it popped up. It's like the pullback of the canonical Maurer-Cartan form, either with the left or the right one, by the map J. So that's the same thing. So we can now consider these kind of like more general class of momentum maps, which would be maps from a symplectic form, not into the dual of the Lie algebra, but in some kind of like more bigger class of Lie groups, such that if you take the Lie algebra of that G star, you get the dual back as an abelian group. Momentum maps with values in groups. That's kind of related to this picture of the quasi-Hamiltonian spaces that we were seeing before, except that we now look at really like infinite dimensional groups acting. And I actually don't have any like a particular example where the dual would be not abelian. So today we really discussed about, in the previous talk it was really about like a non-abelian dual group, but I don't know of any example where the dual would be classically like a non-abelian group. So I would be very interested in like finding examples of that sort, where we really need to pass to the dual group, like to an integration of the Lie algebra, but something that is not abelian. So that would be very cool to find. And since there are quite a lot of people here that ask me continuous questions about Poisson structures, at least one word I would like to say, because I said that in my abstract. So there's some kind of like hierarchy that you can consider if you're interested in Poisson structures. And the first one is like at the bottom, is you have a Lie bialgebra, which is kind of saying that you have two Lie algebras, which are kind of put in duality, such that the commutators works nicely together. So one of them I denote by the dual, but that's like in general, you have like two Lie algebras which are nicely fitting together so that you can form, again, a Lie algebra structure on, like, if you take both of them together. So that's what is sometimes called a B-algebra or a Manin triple, which is like very much connected to that. And you can integrate these ones to Poisson Lie structures, assuming that we have like Lie groups that integrate each of these algebras. We can integrate them to a Lie Poisson or Poisson Lie. I always mix that up. I think it's Lie Poisson. However we want. Okay, sorry. So I really don't. I'm not good at with names. I always like. So you can integrate them, or under some conditions, you can integrate them. But you can always differentiate, like if you have a pair of Lie Poisson Lie structures, you can differentiate them to get a B algebra. And there is something called, once you have a Poisson, Lie Poisson structures, you can integrate them by what is called the tracing actions. Yeah, I call them co-conjugation actions in general. I don't know if they have like a better name, but it's essentially actions. If you take the derivative, then you get the dual of the adjoint. So it's like the adjoint action, you can obtain them by taking the derivative of the conjugation action. And these like tracing actions have the property that if you differentiate them in the correct slot, you get the dual of the conjugation action, I mean the adjoint. So that's why I like to call them co-conjugation. And there's a general structure that you can take the derivative. You can take the derivative of these conjugation actions. So that would be actions of D onto a dual, and similarly of the dual onto the group. And if you take the derivatives, then you get the Poisson Lie structures, and if you take another derivative, you get Lie bialgebras. So the reason why I'm talking about these derivatives is the following, namely that we have a nice action of the diffeomorphism group on here. So you can go back to this example where we have action of diffeomorphism groups that preserve the volume that acts naturally on H2L just by Polberg. So if I have a diffeomorphism and I take a bundle of connection, then I can associate it to that Polberg bundle and the Polberg connection. That gives us a nice action of the diffeomorphism group of that on that space of principal bundles with connection. So now I can apply this hierarchy, which I consider as like the action of G on the dual. So I take the derivative and I get a Poisson Lie structure. And if I do that, then we get a nice map, which is a map from the spatial gauge equivalence classes, and I want to define a Poisson tensor. So I need to say, give it like 2 additional slots. So that would be the vector fields on of the volume. So that, and we need to produce a number. So what we do is we have a principal bundle with connection, and we give ourselves 2 vector fields on L. And essentially, like the natural connotation, like just putting together all the symbols that you have in a natural way. So we need to produce something that eats 2 vector fields. Natural choice would be a true form. So we need to produce a true form out of a connection. So we take the curvature. Take the curvature of the connection, we plug it to 2 vector fields. What we end up with is a function on L, and then we integrate that over the volume form that we have. And if you know a little bit about the diffeomorphism group that preserve a volume, then this one here is the Degenerate cocycle. Cocycle on vector fields that preserve the volume form induced by a true form, which is the connection. And the structure here, this one is a Lie-Poisson structure on this dual space. So I have an infinite dimensional Poisson Lie group that, like, if you write down what the Poisson tensor is, has this form. And it integrates this cocycle on the Lie algebra. So there's a lot of things that I don't understand about, like, the setting. For example, there's certain results that the Degenerate cocycle can be integrated to a nice central extension. And the results that we have so far is that if it has to satisfy a certain integrality condition, and this integrality condition is more or less like equivalent to saying that it has to be the connection of a one form. So for some reason, under the same conditions, we can integrate also this Degenerate cocycle to Poisson Lie structure under that space. So there seems to be like a very tight connection between these principal U1 bonds with connection and like the Degenerate cocycle, the Lie-Poisson structure, and all of them come kind of like nicely together. But I really don't understand, for example, why we can integrate them to Poisson Lie structure exactly in the same way when we can extend this central extension to a group. So I have no idea how they work together. For example, I would like to really understand that in full generality, if there's a condition between like integrating central extensions and Lie-Poisson structures, if there's like a nice way to see that in some way that this kind of integration here from kind of like a Lie algebra to a Poisson Lie structures is the same thing as integrating the central extensions. I'm not sure if there's really like something known, but there are a lot of experts here about that, so maybe I'm just missing something. Yeah, so I just wanted to mention this example and maybe end with a slogan for like the is that diffeomorphism groups don't have classical momentum maps. So that's again a bit of provocative and like very generalizing. But the reason is, like, what I want to say with that is that, like, once you pass to diffeomorphism groups, then you need some kind of generalization of the notion of momentum maps in order to capture certain additional invariants. And that's the reason why we need that is like also relatively clear, because the diffeomorphism group is kind of like able to detect, of course, the topology of your space. But we all know that like topology is usually measured in something discrete, like you say Betty numbers or certain numbers. So very discrete information is usually the invariance of your topology. So in some way that says like the conserved quantities of diffeomorphism actions should be also able to detect something discrete. But there's nothing able to store like discrete values if you map into like a continuous dual space. So in that way, we need to kind of like non-discrete values. In this case here, where we say like, okay, we look at some covering of the Lie algebra into like a group. And that like discrete values then give you a certain space to store like this like discrete topological invariance that the diffeomorphism group is able to. It's, yeah, let's say it like usually what happens is that you can restrict to a certain smaller subgroup. For example, in the symplectic morphism, you restrict to the Hamiltonian diffeomorphisms. Usually there you have an equivariant momentum map. Then you can go a little bit more if you, sometimes it's possible under certain conditions to extend that equivariant momentum map to non-equivariant momentum map for the whole symplectic morphism group, but usually under additional assumptions on the topology. And then if you want to remove even these conditions, then you end up with like, it's just not possible to get like a classical momentum map. So it's like, yeah, the equivariance, it's kind of like in between. It's like sometimes you are able to give it up and still get a momentum map, but if you, like usually it's even not then enough to just get a momentum map. I still have 15 minutes. Okay.
A remark. If you have a non-equivariant momentum map,
yes.
In the book by Lieberman and Marl,
okay,
there is the following procedure described. The non-equivariance gives rise to a 2-core cycle, and this 2-core cycle can be used to make an affine action out of the adjoint action on the dual of the Lie algebra.
yes.
And with this affine action, which uses then this co-cycle,
yes,
the momentum mapping becomes equivariant.
Yes. So that's the standard way to deal with that problem of non-equivariance. One remark there is that even like in the paper that Cornelia have with Francois, if they calculate the momentum map for the central, like for the exact diffeomorphism volume preserving, then they find like it's a non-equivariant momentum map. But under the same conditions here, we can integrate it to an equivariant momentum map, but like just like integrating the dual. Like it's not like changing the action, but it's integrating the dual to a group. So it's like that's what I don't understand. That's usually people tell you, okay, if you have a not equivariant momentum map, you get a co-cycle, integrate the dual, integrate the group to a central extension, blah, blah, blah. So that's like the classical version. What we do here is like instead of integrating the group to a central extension of the group, what we integrate is the dual to a group. And then kind of like get an equivariant momentum map, but in this more general setting of like group valued momentum maps. So that's like you integrate something different, but they are still talking to each other, and I don't know why they still talk to each other and what is the connection there. But like there seems to be something like why this guy is talking to the diffeomorphism group, and it's like also like the way that, for example, that you can see that this central extension integrates with the Lichtenauer co-cycle is essentially using these kind of differential characters. So yeah, there seems to be like something that they talk to each other very intimately, but like I don't know why and like what is the why that works.
Dual Poisson group structure on diffeomorphism to this dual to this H2 hat.
Thank you for asking that, because like what we assume here is we have a natural action of the diffeomorphism group on H2, and that gives you, via this diagram, something as a Poisson Lie structure. So what we would need is like an action of this dual on the diffeomorphism group, and I have no idea of how that should look like. So the only thing that I know is like you can take the trivial one, and then you get the trivial Poisson Lie structure there. So that's actually like an open question, and I asked a lot of people around, is there like some Poisson Lie structure known on some diffeomorphism groups, which is non-trivial? I don't know. Like no one seems to know something about that. So that would be a very natural question to ask. Like, is there like some way, can we use that in some way to get non-trivial Lie Poisson structures on the diffeomorphism groups? But yeah, we asked like
complexification problem. Right, when you do Poisson Lie groups, you have to have the Lou-Einstein. You have to have the complex Lie group viewed as real do Iwasawa. Diffeo groups, complexify them, good luck. Nobody knows. Probably not.
Yes. So I wanted to talk about that the last 10 minutes, but I also wanted to talk 20 minutes about infinite dimensional symplectic reduction. So let's see. Yeah, maybe at least I give you some ideas about what we do with infinite dimensional symplectic reduction. Okay. So what is symplectic reduction is the following, that we are in the setting we talked about up there, where we have a momentum map, and then you take, say we do a symplectic reduction at 0, so you take the level set of the momentum map, and then you quotient out your Lie group. And the statement is that this guy here is again a symplectic space. It's in general not a manifold because we don't assume our action to be free. So it's what is called a symplectic stratified space. So the stratified space means that we can decompose our space into like nice manifolds which have different dimensions. And symplectic means that each one of them is symplectic. And even more is true that like they kind of like put themselves nicely together so that if the Poisson structure extends nicely to Poisson structure and all of that. So that's in some way the finite dimensional version of symplectic reduction. And in finite dimensions, the proof essentially the following picture is that we take some orbit, and then we would like to go down to the orbit space to get a point, and we need to somehow construct like a chart around that point. So we need to find a chart here. So the natural choice would be that we take like a tubular neighborhood upstairs, and we would like to say that this one, like the tubular neighborhood is somewhere like we can construct it in a way that we can understand what the symplectic reduction doing in the tubular neighborhood. So the way we do that is that you kind of use construct certain model space. And that construction is like using some certain regular symplectic reduction that you can understand very well. And that reference system is essentially you have like the action of the group, and then along the fibers, you have a symplectic form, but essentially it's a constant symplectic form. I'm lying a little bit, but essentially that's like morally speaking what's going on. So you construct this model space, and then you use the Darboux theorem to kind of glue this model space into your original manifold. And the model space was created by so that's the finite dimensional story, that like you construct a nice model, then you glue that into your original manifold, so you understand kind of like the tubular neighborhood, and then you reduce it to a starting symplectic reduction for that space, and that you can do essentially by hand, because like you reduced on the fibers, it's like constant symplectic form, so you can just calculate what comes out. And that gives you then a model for the reduced phase space. So that's like, in a nutshell, what is symplectic reduction doing. The problem is there's like two things that we assume. And the first one is that we do a regular symplectic reduction. In infinite dimension, there's no theorem that says like how to do regular finite, like regular reduction. And the second step is Darboux theorem we discussed. There's no Darboux theorem in infinite dimensions. So this whole proof just like falls apart like completely if you look at that. Like there's absolutely no way that you manage to make that proof work. At least, yeah. At least I don't know how to make it work in any way. So that so the finite dimensional proof in infinite dimensions just doesn't work, and we need to come up with something completely new in order to make that work. And the idea is instead of having like this constant, maybe the basic idea in infinite dimensions is the following: that okay, yeah, we start with the same problem. We have some curved orbit, and we would like to understand the neighborhood around that. And the first idea is that we choose what is called a slice for the action. Slice that kind of gives you a transversal thing to the action, but we don't assume that it's compatible in any way with the symplectic form. So, but once we have that, we get like a nice tubular neighborhood, and at least we are able to kind of straighten out the G action. So the G action is nice and like kind of like straighten using the slice, but here in this case we had that the symplectic form was also straightened out with the Darboux theorem, which is not the case here because the slice might be very bad with the symplectic form. So this one means that we have a non-constant symplectic form. So that's like the first step is using a slice. And there's like some results about also infinite dimensions when actions have slices. So that's relatively well covered, and it's fine to assume that we have a slice. The next idea is that because the symplectic form on this tubular neighborhood is not constant, we kind of don't get a nice normal form for our momentum map. And that normal form was used here in this setting to really do the symplectic reduction for this model space. But what we can do is like we can decompose the momentum map. And the decomposition is essentially into two parts, which is regular and something singular. And the regular part has this property that it's essentially linear map in suitable coordinates. To really write down what it means in a full generality probably takes too much time, but I think we can time for like discussing one example where we can see that quite well what happens. So the example, the following, where we look again at like the one forms on a surface, your numbers, and then a symplectic form was alpha, which beta, and then integrating over sigma. And the action was the gauge transformation that acts on that. So the decomposition that I wrote down here comes from a decomposition from the Hodge decomposition, essentially. So we have two Hodge decompositions, namely the first one is of the one forms, and the second one is of the target of the momentum map, which are two forms. And I don't know which way. So the Hodge decomposition of the one form says that we have the dual of the two forms plus some part of the zero forms plus some DRAM cohomology class. And similarly here, we can get decomposition of the two forms into the second DRAM cohomology and the exact forms. And the momentum map here, in this case, is taking alpha and then plugging in d alpha there. So in this case, if you decompose these spaces, what you end up is that your momentum map essentially is a map that is over here. Just the first slot is mapped to the first slot here. The regular part. And it's like, it's d or something, so it's like already completely, in this simple case, it's completely in this form where we only have a regular part and no singular part. So the singular part comes in if I now change my setting slightly, and instead of looking at one forms with values in the reals, I look at like one forms in some non-abelian Lie algebra. In that case, I have to change my momentum map and get like a quadratic correction terms, which is the curvature of the one form, which gives you this quadratic extra term. And now, if you look at like this problem here, then the alpha essentially is the regular part, and now this guy over here is a singular part.
Position of omega 2. There is d omega what?
D of omega 1.
Yeah.
So the exact ones, and then you have like H2, which is just.
But then you get only the closed ones.
Yes. So the point is that in the Euclidean case, we just get only the exact ones. But now the point is with the singularity, with in the case of the non-abelian ones, we get like a singular map. But essentially, that singular map is a map from H1 to H2. So that's singular part. I'm lying a little bit here because there's actually some dependency of the singular part also on these other elements here. But the point is that at the end of the day, I want to set the image to 0. Then the regular part, because it's a linear isomorphism of these two terms, kills essentially the contribution of this one. That has to be 0 because we set it this to 0. This one always has to be 0 by some equivariance. And then the only interesting part that is like still needs to be understood is this map from H1 to H2, which is of this quadratic form. And in this setting here, we can kind of like make it work out by hand because it's like nice. You have this form already in regular and singular. And the surprising part is that we can always do that. Like there's always one part which is kind of like a linear isomorphism, and then some singular part which we don't really know, but like we can split it off. And the third result, or like the third step, sorry, I'm already over time. The third step is that to show that the singular part is a momentum map for compact LIGO acting symplectic vector space. So the point here is that, like, even if you know how to control or like split off the singular part, you need to control the singular part if you want to say something about the manifold structure downstairs, because that might kind of blow up and like be cubic, and then you have absolutely no idea what these how the singularities look like, and then you can never get something as a stratified space. So the idea here is that we get some additional information from the fact that like our original map was not an arbitrary map but a momentum map. So we can now kind of like go through this reduction procedure to see that the singular part is a momentum map, but now we reduce the problem to a compact Lie group action on something with a constant symplectic form. So it has to be a quadratic. And that quadratic gives us enough information to really push down like the whole procedure of symplectic reduction, singular symplectic reduction, also in infinite dimensions. So one more remark about that is that usually the singular map, or like the interesting part at least, is between two finite dimensional spaces. So here it's really from H1 to H2, and that comes down because there is an elliptic complex underlying this problem. And yeah, that's one of the nice results where you can actually see why we get, for example, a finite dimensional quotient at the end. It's because the only thing that survives are essentially H1 and H2, or map between these two. So it's like reduced to a finite dimensional space. And that kind of explains, for example, why we have these nice models for like gauge transformations modulo flat connections modulo gauge transformations, why that should be a finite dimensional space. And that comes like essentially because it's like a map from H1 to H2 that is kind of like plain in there. Of course, like the linear model would be a map from H1 to H2. Good. I think that's all I wanted to say about that. And if someone asks me something about like complex geometry, either now or in the break, I'm happy to tell you more about it.